Welcome to Chemistry Travels. So in the previous videos, we have been looking into the several factors that affect the rate of a reaction, and now we're moving on to the last factor that can alter the rate of a reaction, which is catalyst. So let's look into the effect of catalyst on reaction rates. So for this, we'll have to look into the energy profile for a reaction, which we already saw in our previous video. So this is the energy profile, which is a graph between potential energy and the reaction coordinate. And let's just consider the red graph, the red mountain shaped graph for time being, where my reactant is getting converted to products through the formation of an activated complex. This is an unstable intermediate complex that readily gets converted to my product. Okay. And we saw that the energy gap between my activated complex and my reactant, this energy gap that is represented by the blue line, is called the activation energy, represented by EA, and only those molecules in my reactant species whose energy is greater than this activation energy can cross this energy barrier, form the activated complex, and further form the product. And those molecules whose energy is lower than this activation energy could not cross this energy barrier or form the product. Okay. Now this red one is the case when you have the reaction being done without any catalyst. But now consider the case where you are performing the reaction in presence of a catalyst. So what happens? How does the catalyst affect this profile, energy profile? So that is represented by the black dashed graph that you can see. Now as you can see, in presence of a catalyst, my activated complex is now formed at a much lower energy. The energy of the activated complex has reduced, or I can say that the activation energy, the energy gap between my activated complex and reactant has reduced to this green line, which is represented by EA hash. So now the activation energy has reduced, which means most of my molecules in the reactant species now would have sufficient energy to cross the energy barrier, or would have sufficient energy to reach this activated complex state and further form the products. So as a result, the overall rate of my reaction would increase. So in simple terms, I can say that a catalyst is something that can increase or accelerate the rate of a reaction. And sometimes a material that decelerate the rate of a reaction or reduce the rate of a reaction is termed as negative catalyst. While in some places you can see that such materials that reduce or decelerate the rate of a reaction is termed as inhibitors. Okay. And another thing that is to be noted is the reactant energy and the product energy. It remains the same with and without catalyst, and the only change in energy occurs for activated complex. Okay, let's now move on to enzyme-catalyzed reactions, because enzymes are biological catalysts, and we'll be looking into the kinetics of such enzyme-catalyzed reactions, or in particular the Michaelis Menten equation. So here we have our enzyme and substrate that reacts to form the products, and we know that this occurs somewhat similar to a lock and key model where my enzyme and substrate come closer to each other and fit exactly, which is similar to the case where a lock and key fits perfectly, right? So this particular reaction is not a single stage reaction, rather it occurs in two different steps. So where we have my step 1, which is the formation of an enzyme substrate complex. My enzyme and substrate react to form an enzyme substrate complex ES, and the rate constant for this reaction is termed as K1. Now this is a reversible process where my enzyme substrate can revert back to the enzyme and substrate as individual components, and the rate constant for this particular reversible reaction can be written as K-1. And now we move on to the second step, where the formed enzyme substrate complex would now decompose to form the product and leave behind the free enzyme as E. And this particular reaction has a rate constant K2. Now if we have to write the rate for this particular reaction where my enzyme and substrate give rise to product, the rate of the reaction for multi-stage reactions would depend upon the slowest step. So, or the rate determining step is the slowest step out of these two. Now out of these two, if you look, my first step is a very fast process, while it is my second step which is the slowest. And slowest step being the rate determining step, I can consider my step 2 to be the rate determining step. So I can write the rate of this particular reaction based on step 2, where my rate equal to the rate constant K2 into concentration of the reactant, which is ES here in this case. So rate equal to R equal to K2 into concentration of ES. Okay, this is equation number 1. Now let's see how from here we can derive the Michaelis Menten equation. So for that, we need to consider the steady state approximation. So we are applying the steady state approximation to my ES, that is enzyme substrate complex. Okay. So what does the steady state approximation say? So according to the steady state approximation, the rate of formation of this ES, the active enzyme substrate complex, the ES rate of formation is equal to its rate of decomposition. Rate of formation of ES equals to the rate of decomposition of ES, or if I bring it to the other side, I can say that rate of formation of ES minus rate of decomposition of ES is 0. Okay. So in that case, I can write rate of formation of ES. Now out of all these reactions, rate of formation, ES is being formed only in step 1 forward reaction. So rate of that reaction is K1 into concentration of E into concentration of S. So I wrote the rate of formation step minus rate of decomposition. Now there are 2 steps where ES is being decomposed. The one is the reversible direction one for step 1 and the forward equation for step 2. So for this step 1, the reversible equation, let us write what is the rate. It is K minus 1 into concentration of ES. Now minus, we have one more step, that is rate of decomposition of ES, which is K2 into ES, and rate of formation minus rate of decomposition, totally it is equal to 0. So I have written that, and that turns out to be my equation 2. Okay. Now the total enzyme composition, the total enzyme concentration, which can be written as E total, is a sum of this free enzyme that is being liberated plus the enzyme substrate that is reacting. So we have E, concentration of E plus concentration of ES to be my total enzyme concentration ET. So from this, I can write my concentration of E, concentration of enzyme, to be ET minus ES, where E is the free enzyme and ES is the bound enzyme. So my free enzyme concentration E equal to the total enzyme concentration ET minus the bound enzyme concentration ES, and that can be my equation 3. Now instead of E in equation 2, I can substitute this equation 3. Okay. So now what am I going to do? I am going to substitute 3 in 2. So my K1 into substrate concentration into, instead of this E, I am going to put this term, that is ET minus ES, minus the remaining terms are there as such, K minus 1 into ES minus K2 into ES, and that is equal to 0, right? Now I have to open up this bracket and take the common terms, the terms with ES to one side and the remaining terms on the other side. So when I do that, I would get it like K1 into concentration of S into, I am opening up this bracket, so this becomes ET equal to, I am taking all those terms with ES to the other side. So this comes out to be like K1 into S into ES plus this term goes K minus 1 into ES plus, and this term also goes, so it is K2 into ES, right? Now these 3 terms have ES, so I can take ES common. So finally this equation turns out to be like my ES, I am taking it common, and the remaining terms I am taking it back to the left side. So it comes out to be K1 into concentration of S into concentration of ET by the terms that are without that ES. So that's like K1 into concentration of S plus K minus 1 plus K2. Now we have got an equation for ES, and let this be my equation for 4. And now since we have an equation for the concentration of the enzyme substrate complex ES, we have to substitute this whatever value we got into this rate equation 1, K2 into ES. So instead of ES, we are going to substitute this portion. Clear? So this is the fourth equation for ES. The value for ES is here, and as I told, we're going to put that value into this first equation for rate. So substituting 4 in 1, my rate happens to be this particular K2 is their asset into this value of ES, which comes from this fourth equation. So my rate comes out to be K2 times K1 times concentration of S times ET divided by K minus 1 plus K2 plus K1 times concentration of S, and that happens to be equation 5. Let's label it as equation 5. Now you are going to divide the numerator and denominator of this particular fifth equation by a factor K1. So when we do that, the rate turns out to be from the numerator. Now since I am dividing by K1, this particular K1 is gone while the remaining portion is their asset. So it is K2 into concentration of S into concentration of ET. Now coming to the denominator part, since I am dividing that also by K1, it would be K minus 1 by K1 plus K2 by K1 plus, from this term K1 and K1 cancel, so it would be just S. So I can write it as K minus 1 plus K2, these two would have that K1 there as such, plus from this term K1 is gone, so it's only the substrate concentration. Now this K minus 1 plus K2 by K1, this particular thing that we have in the denominator, that can be represented by Km, which is my Michaelis constant. This K minus 1 by K2, K minus 1 plus K2 by K1 can be represented as Km. So when I put it as Km, my rate would turn out to be K2 into substrate concentration times the total enzyme concentration divided by Km plus substrate concentration. And this particular thing that we have is my Michaelis Menten equation. So this is equation number 6, and the sixth equation is my Michaelis Menten equation, where Km is the Michaelis Menten constant. Now let's consider a situation where all of my enzyme has been reacted. That is, my substrate is present at a very high concentration. So the substrate uses up all the available enzymes. Now the total enzyme concentration ET becomes equal to the enzyme substrate concentration, because there is no free enzyme that is left unreacted. So ET equal to ES concentration, and we saw from equation 1 that rate of the reaction was equal to K2 times ES, right? And this was our equation 1. So now to write the rate of the reaction when all the enzyme has been reacted, the rate would be the maximum. Since all the enzyme concentration has been completely used up, we can say that the rate of the reaction is Vmax now, maximum rate Vmax, that is equal to K2 into ET. Instead of ES, now it is ET. Okay, this is equation number 7. Now from Michaelis Menten equation, we had equation number 6, where rate was equal to K2 times ET times S by Km plus S. This was our Michaelis Menten equation, and in that we have term K2 times ET, right? And K2 times ET is Vmax here. So you can just replace this K2 times ET in Michaelis Menten equation with Vmax. So rate becomes equal to Vmax times concentration of substrate by Km plus substrate concentration. And this is equation number 8, and this is the rate when all of the enzyme has been reacted completely by the substrate. Okay. Now there are 3 different cases that you can consider from this particular equation. So case 1 is when my Km is much larger than substrate concentration. So in that case, the substrate concentration can become negligible, and it can be almost equated to 0. So the rate becomes equal to Vmax by Km times substrate concentration, Vmax times substrate concentration by Km. Or I can also write it as rate equal to K dash into S, where my K dash is Vmax by Km. Okay, this particular term I am just representing it by K dash. Now this is a rate equation for first order, because rate being directly dependent on the reactant concentration, that happens for first order reactions, right? Now we have a case 2 where my Km is much lower than the substrate concentration. So in this case, I can ignore the Km factor. Km can be equated to 0. And from equation 8 now, rate becomes equal to So this Km goes, so it becomes Vmax into substrate concentration by substrate concentration. So both the substrate from numerator and denominator cancels out, giving rise to the rate being equal to the maximum rate, that is Vmax. And now rate being just a constant and being independent of any concentration happens for zero order reactions. So I can say that in this case my reaction becomes zero order. Now we can also have a third case where my Km and substrate concentrations are the same, Km equal to substrate concentration, and in that case, so rate from equation 8 we can get rate equal to Vmax times substrate concentration by substrate concentration plus substrate concentration, because Km is also equal to substrate concentration. So it is 2 times substrate concentration, and S and S cancels from top and bottom. So rate becomes equal to half of maximum rate, or equal to half Vmax. Okay. And this is how we can graphically represent these 3 cases. So it's a graph of rate versus substrate concentration, and as you can see, initially the rate increases with increase in substrate concentration, but over time after a particular point slowly the rate starts to be independent of the substrate concentration, and it turns out that further increase in substrate concentration does not affect the rate. And the first portion of this graph, the initial portion, can be considered as case 1, where my rate is linearly increasing with substrate concentration, and hence the reaction behaves as a first order reaction. But towards the end of the graph, as we approach the end, you can see that this is case 2, where my rate is independent of substrate concentration and my reaction is behaving as a zero order reaction. And whatever is the rate that corresponds to this portion, zero order, that constant portion, that particular rate is the maximum rate. From case 2, we saw that the rate for zero order reaction, rate equal to Vmax. So at this particular point, whatever is the rate, that's the Vmax. And we also have a case 3, that is where rate equal to half Vmax. So if this is the total value, this total portion of y-axis is Vmax, half of that would be half Vmax. So that would correspond to half of that. At that point, you would have the third case, that is at somewhere over here we have our rate to be half Vmax, the third case. And for third case, so the correspondingly the substrate concentration would be equal to Km. So at half Vmax, my corresponding substrate concentration can be represented as Km. Okay. Now another thing is, why is it that my reaction, my enzymatic reactions behave as first order at lower substrate concentration, and why does it behave as zero order in case of higher substrate concentrations? So initially when you have a very low substrate concentration, so you will have your enzymes and your substrates would come and attack these enzyme positions. So it would bind with the enzymes, and not all the enzymes would be occupied because you do not have too much of substrate concentration. So whatever is available, those would come and take up some positions with the enzymes, right? It will bind with the enzymes and you will still have so many unoccupied enzymes. So as you keep increasing the substrate concentration, these new substrate molecules can now come and occupy those unoccupied sites, and reaction can keep moving forward. So rate also slowly increases, right? But consider the case when my substrate concentration is already very high. When it is already very high, all the enzyme sites would be completely occupied. You wouldn't have any unoccupied enzyme sites. So further increase in substrate concentration would not, those substrate molecules would not have a position to occupy, because already everything is occupied and you do not have position to accommodate any new substrate molecules or to cause further increase in the reaction rate. Okay, so the reaction turns out to be independent of substrate concentration, and hence you can say at higher concentrations it is zero order. And finally, instead of using this plot to find the value of Vmax and Km, we can have another easier method, which is the Lineweaver Burk method. So according to the equation that we already had, my rate was equal to Vmax times substrate concentration by Km plus substrate concentration. We already saw this equation. Now, and it was from this equation we had the 3 different cases and we came up to this graph. Now, this particular equation can be reversed. You can write the reciprocal of this equation. So 1 by R becomes equal to Km by Vmax times substrate concentration plus 1 by Vmax. And now this is of the form y equal to mx plus c, which is the equation for a linear graph, right? With y being 1 by R and my x being 1 by substrate concentration. So this is a graph, a linear graph equation for a linear graph. So I can plot this graph linearly in this way, which is between 1 by r and 1 by substrate concentration, and my intercept of this graph is y equal to mx plus c. So the c value is intercept, that is 1 by Vmax, and m is the slope, which is km by Vmax in this case. So from the slope and the intercept, you can easily find the values of km and Vmax using the Lineweaver Burk method. Okay, so that's it for this video, and I hope you understood whatever has been discussed. Thank you so much.